We're now going to solve the second part of the example problem, and that is to evaluate the amount of exergy destroyed. And remember I said that there were two ways that we could go about doing this. When we're doing exergy destroyed, we have two ways. We can look at entropy generation as the first method. So there we have exergy destroyed is equal to the surrounding or ambient temperature multiplied by the generation. Or we can do the exergy balance approach. We'll start with the one of calculating the entropy generated and then computing exergy destroyed that way. So we'll begin here with little exergy destroyed is equal to the surrounding or dead state temperature multiplied by the entropy generation term. So we need to evaluate or calculate entropy generated. So the expression for that is the following. Now we're dealing with a nozzle that we said was adiabatic, and consequently this heat transfer term drops out, which makes our lives a little simpler. And the other thing that I'm going to do, I'm going to divide by the mass flow rate from both sides of the equation. And when we do that, what we get is little s gen is then equal to S exit minus S inlet. So that would be the entropy of the steam coming in, exiting minus the steam coming in. We can then evaluate that using the values that we have in the steam table, or that we pulled out earlier in the problem. Now for exergy destroyed, we take the entropy generated and we multiply it by the surrounding temperature. Surrounding temperature was 25 degrees C, which is 298 Kelvin. And when we do that, we get exergy destroyed is equal to 6.29 kilojoules per kilogram. So that answers the question using an entropy generation approach. The second approach that we're going to look at is that of the exergy balance. And for the exergy balance, the equation that is the equation for a single inlet, single exit, as well as for steady flow. With this, we know that we're dealing with an adiabatic nozzle, so that disappears. Nozzles don't do work, so that disappears. And the final relationship then turns out to be exergy destructed, or destruction, equals mass flow rate times the change in exergy of our flow stream. Now what I'm going to do, I'm going to divide by mass flow rate on both the left and the right hand side, and that will convert this into a smaller x for exergy. So we have that expression there, psi 1 minus psi 2. What we're now going to do, we're going to expand this by putting all the different terms that consists of. And so we get the following. Now here we can cancel out our potential energy term because the nozzle is not moving in the vertical in any way, shape, or form. We have to keep the velocities because they are there. So what I'm going to do now, I'm going to plug in the values that we extracted when we looked at the steam tables at the very beginning of the problem, and I'll plug them into this equation. And remember, you have to be careful with these. Whenever you're mixing enthalpy, entropy, and velocity, we need to account for the fact that velocity is in joules, whereas entropy and enthalpy will be in kilojoules. And so in order to correct for that, what I do is I multiply by 1,000. Again, multiplying by 1,000 to correct for that difference. So plugging in all of the values, what we end up with is exergy destroyed is equal to 6.30 kilojoules per kilogram. So that's the answer to the third part of the problem using the second approach. Let's take a look back at what we got when we used the previous approach. We obtained 6.29, and with this new approach using the exergy balance, we get 6.30. So you can see the two approaches agree, more or less, off by 0.01, but that's not that big of a deal. It's probably a round off error somewhere. Consequently, we see both approaches work. So now what can we say about this? Why are we getting exergy destruction with this nozzle? Well, most of the exergy destruction is due to entropy generation. So where is the entropy coming from? Where could we have entropy generation within a nozzle? Well, for that, what you're going to have to do is think back to your fluid mechanics course. Either you're taking one now or you've taken one before. But when you look at fluid mechanics, what this means is that this nozzle is probably not that well designed. We'll always have some entropy generation no matter what we do. But this could be there because we have a poorly designed nozzle from a fluid mechanic perspective. So from a fluid mechanic perspective, what are we looking for? We're looking for a number of things. So you could say these are the design requirements. We want the exit flow from the nozzle to be uniform. We want to avoid separation inside of the nozzle. That means we do not want the boundary layer to separate off the wall. You usually want to have it a minimum length because you don't want to have a long nozzle. And another thing, we want to try to minimize the boundary layer thickness at the exit because that will help give us a uniform flow. So let's take a look at two different types of nozzles. Let's say we have a nozzle that's like this. Now what might be happening here? Well, if we were to draw our streamlines, sometimes what you can get in here, you can get flow separation along the walls depending upon the pressure gradient that you have along the wall of the nozzle. If you have a pressure gradient that is so strong that the flow in the boundary layer right along the wall of the nozzle comes to a stagnation point, that is the velocity is zero, you will have the boundary layer lift off and you have separated flow. So that might be a bad nozzle, but let's say we were to draw or design a nozzle that looked like this. Well, here it's nice and smooth. We're probably not going to get any separation. However, here what's going to happen is our boundary layer is going to get very, very thick. If we were to look at the velocity profile along the wall, we'd have a very, very thick boundary layer, and consequently, again, we don't have a uniform exit. So those are places where you can have inefficiencies, and separated flow leads to turbulence, and that leads to viscous dissipation, which is basically conversion of pressure into thermal energy, which we said is a disorganized state of energy. So this here would be the process of entropy generation. Now, there could be other ones that are at play as well, but this would probably be one of the larger and more significant ones. So that gives you some background into terms of why this nozzle may be behaving the way it is that we see, where there's actually exergy destruction taking place. So with that, I'd like to conclude the lecture. Thank you for your attention. Bye-bye.